Okay, Honors Geometry, Thursday, the 27th of February, 2020. 4 months from today, guys, for those counting. Okay, SWBA students will be able to simplify radicals, use the Pythagorean theorem, and its converse, section 6.1. What?
7.1.
You guys are so weird. Yes, 7.1.
I even talked about it.
I did that for all of
Yeah,
them.
I noticed the time. For everything?
Everything.
Oh my goodness. Section 7.1.
Y'all are weird. That was so funny.
Keep it moving.
We can pick.
Oh no.
That looks like an N.
Did anybody see that? Okay, that was not my fault.
It's always your fault.
I
Oh,
tried
of
to
course.
warn you. What is happening?
Celebrate it.
It's rebelling against me.
Oh,
I don't
blame
know.
it.
It is. How is my eraser? What's happening?
Oh.
You're out the door? Oh.
Yeah.
Maggie, you're missing the rise of the machines. Okay. Let's see if I have this thing under control now. Okay, so Pythagorean theorem is converse 7.1. Okay, so simplifying radicals. We just practiced this a little bit during our warm up. Okay, this is an algebra 1 concept, bringing it back. Okay, and as you heard Taylor complaining earlier, it is an algebra 2 concept as well. Square root of 8. So we want to check for perfect square factors because we're doing square root. So you can say the square root of 8 is the square root of something times the square root of something. So what do we want to call it? Square root of what times the square root of what? Well, we want to look for perfect square factors because if there's a perfect square, we can end up saying, oh, well, the square root of this number is this. Like the square root of 9 is 3. We can't know what the square root of 8 is exactly because we don't know. 8 is not a perfect square. Nothing times itself is 8. It's a decimal that goes on forever. So, is it reasonable to say that 9 can be a factor of 8? No, why not? It's over it, right? So what's the first number we should start with?
4.
4. Is 4 a factor of 8?
Yes.
Yeah, how many times?
2.
2. So the square root of 8 is the same thing as the square root of 4 times the square root of 2. It's the same thing as the square root of 4 times the square root of 2. Now the reason we call it that, we change it just to look like this, is what is the square root of 4?
2.
Normal 2. So you say the square root of 4 is normal 2. We don't rewrite the radical there because you don't need to. You don't have to rewrite the radical because we just took the square root of 4. Just like after you square something, you do 2 squared. You don't write 4 squared, you just write 4. Okay? So you have 2 times the square root of 2. And we can't simplify square root of 2 any more than it already is. And so this is our answer.
Oh.
It is. Oh. Psych. Okay. Square root of 108. Okay? So what number should we start with for checking to see if it goes into it?
81.
Probably 100. That's the first perfect square that's lower than it. We're only trying perfect squares because our goal is to be able to take the square root of a number. So does 100 go into 108?
Yes.
Not even amount. We want an even amount. We want a normal amount, like it divides into 8. Does 81 go into it?
No.
64?
No.
49?
No.
36?
No.
Yes.
How many times?
3.
How can you check it to see if it goes?
Divided by 36.
Yeah, you can divide by 36. You can take your calculator and divide by 36.
Operation big.
What is the square root of 36?
6.
Normal 6. So we have 6 square root of 3. So it's a lot easier for us to know what this is. It's when it's 6 square root of 3 than the square root of 108. That makes it a lot more realistic to us. Okay. 4 times times the square root of 125. We had the same kind of thing like this in our warm-up. This is the one that Justin ended up coming up and doing for us. Okay. So here, there's like a 1 in front of the radical. And so we had like a 1 times the square root of 36 times the square root of 3. So you have like a 1 times 6, which ends up being 6. Same thing here, instead of a 1 though, it's 4. So when you have a number come out of the radical, we find our perfect square, we'll multiply that with that 4. Okay, so is 125 perfect square?
Yeah.
Okay, does 121 go into it? No. 100?
No.
81?
No.
64? 40? 49?
No.
36? 25?
Yes.
Hey, ha ha ha. How many times does 25 go into it? 5 times. 4 times the square root of 25 times the square root of 5. What is the square root of 25? 5. 4 times 5, because these are multiplying, they're still multiplying now, and it's a normal number. Times the square root of 5 is still hanging out there. What is 4 times 5? 20. Square root of 5, and that's as simplified as we can get, because we cannot simplify this. Cannot simplify the square root of 5 anymore. Really, really. Okay, we're going to be simplifying radicals the whole time in this chapter, by the way, so we're going to have to get reused to it. Okay, yes. Like simplifying radicals. You might not use this one in real life. We use it in other math though. So it can be used. Carpentry stuff, I guess. Engineering stuff, architectural stuff, some stuff like that. Could be used in for square roots. You might just estimate it with a calculator still, but if you need to know the exact number, this could be helpful. Some science applications for darn sure. So if you're going to do measuring stuff, lab work, sometimes you might use this as well. So maybe there. Yeah. And yeah, it just helps us keep our numbers more exact than if we type them into decimal. Because the moment we type this into decimal, we get a never-ending one, and then we have to start rounding. And so this helps our number look cleaner without yet approximating. Because this is still exactly this number, because it's the same exact number, but if we round, then it's no longer the exact same number. And sometimes you just need to be really exact, especially on like science or like building things. So, good question. Multiplying radicals. So we can go the other way, kind of. Square root of 3 times square root of 2. We can multiply those since they're both under the radical. And you get the square root of what? 6. You get the square root of 6. And it can't be simplified anymore, so we just call it square root of 6. Okay? Now, what we end up doing here is essentially 1 times the square root of 3 times 1 times the square root of 2. So 1 times 1 is this 1 out here. So here, let's see what's written down after. Let's forget. What is 3 times 7? 21. And what's the square root of 5 times the square root of 5? The square root of 25, which is also the same thing as square root of 5. That should be 21. Square root of 5. So we have 21 times normal 5, which is 105. Okay? So we can say the square root of 5 times the square root of 5 is normal 5. Or you can say square root of 5 times square root of 5 is square root of 25, ha ha ha, which is normal 5. So anytime you have two of the same square root multiplying with each other, you use the normal number, 5, every time. Okay. F2 over the square root of 3. We don't want a radical in the denominator. We don't want a radical in the denominator here. Okay? So what we want to do is we want to get the radical out of there. So what we do is we end up choosing to multiply by the same exact radical that's there. So we multiply by the radical 3 over the radical 3. Square root of 3 over square root of 3. And we choose the same exact radical as what's already there. So we choose the same exact radical as what's already there. And the reason why we do that is because of what happened on letter E. Because what is on the bottom? What is the square root of 3 times the square root of 3? Square root of 9, which is 3. So we end up getting rid of a radical. We don't have a radical anymore. On the bottom now we just have a normal 3. On the top, 2 times the square root of 3 is just 2 times the square root of 3. We can't call it 6 or the square root of 6 because 1 is underneath the radical and 1 is not. So we just have 2 square root of 3 over 3. You have 2 square root of 3 over 3. My number just disappeared here. Pretty backhanded, I'll take it anyway. So, what was I gonna say? I was gonna say something. What was it? Oh, square root of 3 over square root of 3. What is square root of 3 over square root of 3 actually equal to? 1. So we just multiplied it by, everyone come hands, 1. Multiply it by 1. We just made 1 look different. So if we multiply something by 1, does it actually change the value of it? No. So that's why we multiplied it by 1. 1. I should have moved like 3 fingers. 1. Because it doesn't actually change the value of it. We just made 1 look differently for our purposes. So it's still the same number. We just made it look different. Here, 3 over the square root of 12. We want to do the same sort of thing. So, what would we multiply the top and the bottom by?
12.
Square root of 12. And that gives us 3 square root of 12 over what? 12. Or square root of 144, which is 12. Now, can we still simplify though? Yeah, what can we simplify? What? Yeah, by 3 on the top and bottom. The 3 and 12, 3 goes into both. So it becomes square root of 12 over 4. Now here's another thing. Can we simplify the square root of 12? Yeah, it ends up being the square root of 4 and the square root of 3, which ends up being 2 times the square root of 3, because the square root of 4 is 2. And as we get more and more comfortable with this, I'll start skipping the step of actually writing square root of 4 times square root of 3, and just write 2, because that's what the square root of 4 is. And now can we simplify one more thing? Yeah, we can call it square root of 3 over what? 2. It's a lot of work in one box, isn't it? You can use this box too if you want, though, because it's plain. Okay, so on letter H, 9 times the square root of 2 quantity squared. What's it mean to square something? Multiply by itself. You have 2 of them being multiplied together. So this is really 9 square root of 2 times 9 square root of 2. 9 square root of 2, 9 square root of 2. So we multiply 9 and 9 together, we get 81. What's square root of 2 times square root of 2? Normal 2. Square root of 4 is normal 2. So now we take 81 times normal 2. We get what? 162. Now, if you wanted to go back to the algebra 1 exponent concept of saying, hey, if we're taking a product, multiplication to a power, you can take this exponent times the exponents that are here. 9 is being raised to the first. This is being raised, the square is being raised to the first. So you can end up having, say, we have 9 squared and the square root of 2, which is being squared. So 9 squared is 81. And a square root being squared, they undo each other. They're inverse or opposite operations, just like multiplication and division, or addition and subtraction. So we have normal 2. Woo! Okay, that was a radical review. Okay, that was a review over some algebra 1 and radical concepts because we're going to use them this chapter. Okay, so that was our review. Okay, so even if it didn't look familiar, we had done it before. We took some time to review it anyway because we're going to use it a lot. Okay. Okay. Thanks for bearing with me. Okay. All right, triangle. We know it's a triangle with one right angle, right? Here's an example, right triangle. That's not new to us. This is old news. This is just recapping. Okay. Not no capping, recapping. Okay. So a triangle with one right angle. We have some sides there that are labeled A, B, and C right now. Now we have this Pythagorean theorem. This is probably something you've heard of before. In a right triangle, only for a right triangle, if the legs have lengths A and B, the legs are the sides touching the right angle. Okay? If the legs have length A and B, which they do, and the hypotenuse, side opposite the right angle, has length C, then, can anybody tell me what the Pythagorean theorem is? A squared plus B squared equals C squared. Okay. So So in this case, then a squared plus b squared will always equal c squared if it's the right triangle. It'll always be that way. You can't form a right triangle and this not be true. It's pretty neat. You can't form a right triangle and have it not be true. Okay. So just a reminder, guys, that A and B were the legs. A and B were the legs. And that C was the hypotenuse. B was opposite the right angle. What's the other fact we know about the hypotenuse besides that it's opposite the right angle? It's the longest side, always. Which is why we can take the other two sides and square them and add them and have it be equal to the third side being squared. Okay. Questions on that? Okay, you guys ready to use this Pythagorean theorem? Oh, okay. Let's do it anyway, though. Appreciate the honesty. Okay, step 1. Find the length of the hypotenuse of the right triangle. Okay, so we know two of the legs, we don't know the hypotenuse. Anyone want to help me set this one up? Okay, thank you, Kevin, James Soul.
5 squared, which is 25, plus 12 squared, which is 144, equals C.
Okay, or in this case, x
Squared.
squared. So 5 squared plus 12 squared equals x squared. The leg squared added together equal the hypotenuse squared. Does it matter whether we put the 5 or 12 first? No, it doesn't, because we're just adding. Okay, what is 5 squared then? Kevin said it was 25. Okay, what's 12 squared? 144. This equals x squared. Okay. I'm going to set that on my desk and then grab a notepad from the corner of my desk.
How am I, Jake?
How did you take me today?
Okay, where to say this again? Okay, right behind you, John.
Oh, yeah, mine.
So 25 plus 144 equals x squared. What is 25 plus 144?
169.
169 is equal to x squared. Okay. So now, how do we get x by itself? Remember how we undo that square? You square root both sides. You square root both sides. Because a square and a square root undo each other. A square and a square root undo each other. Because what is the square root of x squared? What times itself is x squared? X. X times x is x squared, so the square root of x squared is x. Now, does anyone know what the square root of 169 is? It is 13.
Memorize my times
I had
tables.
a shirt that said I was 169 square.
Oh, when you turn 13,
You were the
that's
square root of
fun.
169?
Yeah,
That's actually pretty cool.
yeah.
Bro, I want to
Okay,
like that.
anyway. So, our hypotenuse is what length?
13.
13. Okay, has to be. Okay, it's kind of neat. Now, if you guys might recall from algebra 1, when you take the square root of both sides of an equation like we just did, you're supposed to account for both the positive and the negative. But here's the thing. Can we have a negative length?
Yes.
No.
No. So we can automatically discount the negative here, because we're talking about length. Because it can't be negative 13 long. It's impossible. Okay, questions on that? Yes.
Why do you have to account for the negative?
Why did it
Normally? Because not only does x times x equals x squared, but negative x times negative, or excuse me, negative x times negative x also equals x squared. And not only does 13 times 13 equal 169, but negative 13 times negative 13 equals 169 as well. So it has two different answers. Yep. Yes, Taylor.
Okay, I know I was wrong, but why'd you get squared?
Yes, we're doing the Pythagorean theorem,
Oh.
which is a squared plus b squared equals c squared. Thank you for asking, Kevin.
So if we weren't doing length, how would you know if it was negative or positive?
You put both. You put positive or negative 13. Yep, good question. Yep. Any other questions on this one?
Can you like keep it up for
On this one. Oh, I didn't ask for questions. I didn't ask for questions of Colonel either, or Chief, or Sergeant. The look of confusion before the look of realization is nice, by the way. Thank you for that. And then look at disappointment from Rowan is a nice side of touch. I get that from a lot of times. So, I get that like every class period. It's pretty good. Yeah.
So
why don't we do plus or minus? 'Cause I know, I mean, like, I
Yep,
know
that's a
one-
great question. So we can have 13 is talking about what kind of thing, what like realistically.
I know it's length, but why?
Length.
I
And you
guess-
have negative length. Reed, you want to grab the notepad on my desk? Okay. And you have negative length. No, so we can just count it. So typically we do have the positive and negative versions, like you're saying, but we can just count it because of the fact that we can't have negative length. So don't worry about it. Okay.
Well, are we always gonna do it like?
In this chapter. Alright, so we have this thing called a Pythagorean triple. You guys can use these, you don't have to use these. I'm not going to ask you to memorize them. But if you want to memorize them, they can be helpful shortcuts. Okay? So I'm not going to make you memorize them, I'm not going to ask you to. I'm giving them to you because they're helpful shortcuts if you want. Okay? So a Pythagorean triple is a set of three positive integers that will always form a right triangle. So if you have these three sides of a right triangle, 3, 4, and 5, or excuse me, the sides of a triangle are 3, 4, and 5, it has to be a right triangle. If the sides are 5, 12, and 13, has to be a right triangle. 8, 15, 17, has to be a right triangle. 7, 24, ha, 25, ha, 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 that's the best one. It has to be a right triangle. And the reason why is because if you do the Pythagorean theorem with these, it ends up working out. Okay? Now, in 3, 4, 5, which one of those would be the right angle, or the hypotenuse? 5 is the biggest. And 5, 12, 13, which one would be? 13. And 8, 15, 17, 17. Now, if we even just check 8, 15, 17 real quick, now let's try to make sure it actually worked. 8 squared plus 15 squared. Does it actually equal 17 squared like it should if this works? Okay, well 8 squared is 64. What is 15 squared?
225.
225. Can anyone tell me what 17 squared is?
I can't tell you.
Oh,
289.
89.
And does 64 plus 225 equal that?
Yes.
Yeah, so this triple does work out. And 7, 24, and 25 would as well. Ha 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 ha. Okay. They all work out. And so there's just triples that have been found. Oh my goodness.
The eraser doesn't work. Fire. Try recalibrate.
It's not the issue.
You know what is on.
It is way off.
How do you should really warm up your room, like how Mrs. Rodriguez does it, because you're probably the coldest.
Go stand in the corner.
We've been,
We've been over this so many times.
Miss Rodriguez puts her thermostat in the freezer. Fridge.
That is literally such, like, that was so smart. Like, I would have never thought of that.
When we walked into her room, it was like another.
And I was so there for it, and then she took it back and tried to
So, here we are. Back where we started. Back where we just were. Let's try this one more time. There we go. Now you can also do multiples of these. You can also do multiples of these. So you can do 3, 4, 5, or you could also do 6, 8, and what do we think? 10. Or you could do 9, 12, and 15. Because we multiply them all by 3. So you can keep going. So if you ever see one of these, and you see two sides are 9 and 15, with the 15 being the hypotenuse and 9 being a leg, you know the other leg has to be 12 in a right triangle. You can even do this one. You can do 14, 48, and 50. Now you might not memorize those as often. Okay. The most typical ones we see are the 3, 4, 5, 5, 12, 13. Those are more common. Okay. But if you see any of these, they're always going to work. So you always know what the other side is. It's pretty neat. Heather, are you asking a question or are you just sitting with it?
I have a question.
Okay.
Would this maybe be a bonus question on our test?
I don't think so. No, it's not.
Promise me.
It's not a bonus question on the test.
What was the bonus question on this test that we just did?
Isn't that fun?
Like, why?
Which one?
The last one.
You don't want
Isn't
to
it
know
great?
how
That's
long
my favorite bonus question I ever asked.
You want to know how long I spent on that question?
No. What?
Like 10 minutes on that question.
Yeah. I'll say people tend to spend the most time on that question sometimes. It's so funny.
That one is the graph one. That
One of my favorites so far. So it was Sarah's. She drew this. She drew a meme. It was like the distracted boyfriend meme. Where like the dude's walking with his girlfriend and he looks back and sees someone else. And it, like I was the distracted boyfriend. It said Mr. Kossel. And then the girlfriend was teaching math. And then the girl that was distracting me was memes. Right? Yeah, it was so good. Sounds like teaching math? Nah, memes. It was pretty great. Yeah. So So that one cracked me up a lot.
I have been used to Miss Rodriguez and her stories.
Yeah, and she's put on there like, you know the meme format.
Yeah.
Like, I do. It was great. So, yeah, that one cracked me
I
up.
think I spelled a couple words wrong, so I'm sorry for my grammar.
I'm sorry for my grammar. It was crossed my fingers. Alright. Example 2. Find x. Write your answer in simplest radical form if necessary. Okay? We're going to keep saying that a lot. Write your answer in simplest radical form. Oh my goodness, how could we find x? This whole thing is in a right triangle. Well, let's work backwards. We see a right triangle here, don't we?
Yeah.
Okay? Do we know this side though?
No.
But if we knew the side, could we find x?
Yes.
Okay? So we need to find this side. What do we want to call the side for now?
B.
B.
C.
F.
Baloney.
Or Y. I'll call it Y. Okay, actually, call
I
me
know
an
how
audible.
we can do it.
I'm doing one I haven't heard yet.
T.
F. You do have, you can't not do that.
Smiley face. We did that last time.
That's okay.
Do a frowny face.
No.
Why not?
Not as happy.
No, it's not.
Yeah.
No, it's not.
How can we figure out smiley face? Great.
Okay, so it's a common triple, isn't it?
Where?
The one.
Left triangle? Which one is it?
3, 4, 5.
3, 4, 5, but multiply, right?
Yeah,
So this is 6, this is 10. What's this have to be?
that has to be 8.
Has to be 8.
Yes.
Could we also have done the Pythagorean theorem to solve for it?
Yeah.
Yeah, so what we would do to do that, I'm not going to make you do it now. What we would do to do that would be 6 squared plus smiley face squared equals 10 squared. Knowing that 6 squared is 36. Smiley face 6 squared is smiley face squared. That was not, anyway, over time that 6 this. Minus and 100. Subtract 36 from each side and get smiley face squared to equal 64. And you square root both sides and you find your smiley face to be 8. Now we know this is 8, this is 12. How can we find x? Now we can use the Pythagorean theorem, right? Okay. So can somebody help me set up this? Actually, no. Yeah. Yeah, can somebody help me set this one up? Okay. Go ahead, Sarah.
8 squared plus 12 squared equals x squared.
That'd be a great setup. 8 squared plus 12 squared equals x squared. We don't care whether the 8 or 12 comes first, but they both have to be the ones added together because they're the legs. Okay. Now back up a second. How do we know this small triangle was a right triangle? This is a right angle, right? So this has to be a right angle. Yeah, that's because it makes a straight line. So now we can solve this one and put it in simplest radical form. I want you guys to solve this one and put it in simplest radical form. When you have it or have questions, raise your hand. In simplest radical form. The simplest radical form is what we did on the first part, that recap. Okay, that's what simplest radical form is. I don't want a decimal. Okay, heads up on the test, it's specifically going to say no decimals. Okay, so heads up on the test, it's going to specifically say no decimals. Okay,
So I can't put a decimal.
correct.
Do I have to like shorten it? Is that what I-
Like we did in the warm up. Or we did during our recap that you missed so far because you were taking the test.
Well, whose fault is that?
Do you actually want me to answer that?
Yeah, it's yours.
Is it? The thing is, I can't trust that you were actually sick.
But it was actually.
I can't trust that you were actually sick. All of us.
There's gotta be an easy way to simplify.
I think it's easy. You want me to check with this one? It's a perfect square that goes Let's try and find the biggest such perfect square because that'll help us get there faster.
Do you have any of those perfect square sheets?
There's a list on your notes on the first page.
They have old notes from when I was in middle school, and they have a perfect square chart covering
Sure. You can't use it on your test, but yeah.
Okay, wait, I'm not sure if this is right. It's kind of whack. I don't know what I did wrong. I could find a big deal. Yeah.
Alright, look.
Oh.
No.
I don't think that's how that works.
I realized that after I said that.
Okay, yeah. I just really suck.
Almost like you see those comments that you were saying, and I'm like,
Oh wait, Mr. Consul. You can still simplify that after what she has.
you know,
Yes, you can. 13. 9 and 4.
those ads would
Oh yeah, they do. They don't want My head really hurts. I do way too much math lately.
always get that. If you're done with 2, you can go ahead and go on number 3 over. So wait, we're doing
Why does it look like that?
on this on 3, I'm letting you round to the nearest 10.
Bless you.
How many is our test? This. Then you know, keep posting minutes. 8, so you know, packet, one thing on the corner of my desk.
How did people do that so fast?
Practice. Let's talk about this one up here on example 2. 8 squared is 64. 12 squared is 144. That equals x squared. So we have 208. That equals x squared. As we see, just take the square root of both sides. We're saying, okay, well, 208 is not a perfect square, unfortunately. The biggest perfect square that goes into it, if we start with 196 and go down, okay, is 16. We want to do the biggest perfect square because that helps us get us there faster. So we get the square root of 16 and the square root of 13, because 16 times 13 equals 208. Square root of 16 is normal 4, so we get 4 times the square root of 13, which is equal to our x, our missing side. It's about finding our biggest perfect square that is a factor of that number. Okay? And so you just want to start with biggest perfect square beneath it and keep going down. Okay? Questions on that? Now you can get there if you had chosen 4 as a perfect square, then you have to do it again. Let's continue. Let's look at example 3. We'll discuss this together real quick. If a tree breaks as shown, what is the original height of the tree? Ground area is the nearest 10th. So we have part of the height, we have the rest of the height, and we have the ground. What What kind of angle would the tree be with the ground? Right angle. Could we make this Pythagorean theorem?
Yes.
Yeah. 15 squared plus 22 making Taylor Swift proud squared equals our x squared. So then we can go, okay, 15 squared is 225. 22 squared is 484 equals x squared. So what's 225 plus 444?
What?
Yeah,
I
I
got
did
709.
709 equals x squared. Now we square root that, and we get x to be approximately what?
Oh, we're doing approximately that? That
Oh,
would make
here we
sense.
can do nearest tenth because I said specifically.
26.6.
So almost every time we'll do simplest radical form. This time I specifically said we could. 26.6. Now here's the thing. Is this the original height of the tree?
No.
No, how do we get the original height of the tree?
You just have 15.
You add the 15, because this is the 26.6 over here. So do the original height to add them both up. And so the original height is approximately 41.6 feet. Ends up being like 26.63, I think it is.
Yeah, 26.63.
That hurt my head.
Because there's a 700 for 2.
It'll only be 26.6, whatever it is. Questions on that?
How big is this?
Think double lady, okay? So, we also have the converse of the Pythagorean theorem because we love converses, okay? So we're saying not just vans but converse, okay? We can use this to check to see if it's the right triangle. So just like we used this on the Pythagorean triple a moment ago, we can actually say, ask the question, does a squared plus b squared equal c squared? If it does, it's a right triangle. If it doesn't, it's not a right triangle. So here, 11, 20, and 23, we don't know if it's a right triangle yet, but we can figure out if it is. Which two would have to be the legs and which one would have to be the hypotenuse?
11, 20,
Yeah. So we check it by doing 11 squared plus 20 squared, and we say that equals 23 squared. So we can tell whether it's a right triangle or not. Okay, and what is 11 squared?
121.
21. So if it satisfies this, then it'll be a right triangle. What's 20 squared?
400.
And what's 23 squared?
529.
Bro, how do you know that? Like,
Oh, because I already did it. So just
Okay. 121 plus 400 is 521. Does 521 equal 529?
Yeah, 8.
No, if you add 8. So is this a right triangle? No, so it's not a right triangle. So is it a right triangle? No.
It's up to.
Now, we might be able to ask, what kind of triangle is it then? So we have this handy thing. So if c squared is bigger, if c squared is bigger than a squared plus b squared, which is the case right now, c squared is bigger than a squared plus b squared, it's obtuse. If c squared is smaller, then it's acute. So no, this is obtuse.
It doesn't tell us what triangle.
That's true.
So we don't have to say that.
Okay.
Nobody cares.
Now, let me say why that we can know it is that way. Okay? You guys remember that flashlight thing we did before? The bigger the angle, the bigger the opposite side. Smaller the angle, the smaller the opposite side. Okay? The same kind of thing there. So, if all of a sudden, if c squared is bigger than the a squared plus b squared, that means c squared is bigger than it should have been for it to be a right triangle. So if c squared is bigger, that means normal c has to be bigger, right? For the square to be bigger, the normal has to be bigger. Okay? So if the normal c is bigger, then this angle opposite had to get bigger. So no longer is it 90, it's bigger than 90, which would make it an obtuse angle, making it an obtuse triangle. Whereas if it gets to be less than 90, then the c squared is going to be smaller because the angle got smaller. Kind of neat. Okay. Can segments with lengths 11.2 inches, 6.5 inches, and 7.1 inches form a triangle? If so, what type? Going back to the last chapter, how do we know if they can form a triangle in the first place?
Two smallest ones added together.
Two smallest ones added together compared to the big. 6.5 plus 7.1, and we compare that to 11.2. 6.5 plus 7.1 is
13.6.
13.6. So does it make a triangle?
No.
Um,
Oh, it has to be bigger.
Yes, so it does make a triangle. Now we need to figure out what type. So to figure out what type, we put it into the converse of the Pythagorean theorem, which is really the normal Pythagorean theorem. And we just check to see what happens. So the two smallest sides again, 6.5 squared plus 7.1 squared equals 11.2 squared. Jeepers. And we just check to see, what do we get? So what is 6.5 squared?
42.25.
Awesome. I'm sure Taylor memorized that a few days ago, but she also could have typed it in the calculator to double check, okay?
Yeah.
What's 7.1 squared?
50.41.
Okay. And this equals what? 125.44. Okay. Is this going to equal though?
No.
No. Which one's going to be bigger? C squared or A squared plus B squared?
This is weird.
C squared, because 92.66 is not bigger, it's less than 125.44. So what happens if C squared is bigger? Is it obtuse or acute? Obtuse. C squared is bigger, so the actual C is bigger, so the opposite angle is bigger. So yes, it's an obtuse triangle. Questions on that one?
Can we not do example 6?
We'll do example 6 so we can talk about it. Okay. Okay. I don't think we'll be able to do it well though. Okay. Can say these statements form a triangle and so what type, same kind of thing. But this time, do we know what 2 squared of 41 is? How can we compare? Which one do we know is the biggest or the smallest? Do we know which one's the biggest? No. Well, what can we do with this? We put it in a decimal so we can compare it. Yeah. So what is 2 squared of 41 approximately so we can compare? Graydon? Okay, so this is approximately 6.4. So which side is the biggest? 10. So does 8 plus 6.4, will that be better than 10? Yeah, so does this form a triangle? Yeah, so now to figure out what type though, we don't want to use the approximate to figure out what type. The approximate's good enough to figure out if it does make one. It's not good enough to figure out the type. So to do the type, we still want to do 8 squared plus 2 times the square root of 41,
Which actually sounds
Squared.
like, doesn't that cancel out the...
and it equals 10 squared. Okay? It is spelled obtuse wrong. Thank you for being patient.
Lit, okay, love you.
So 8 squared, oh Sarah.
To figure out the 2 square root of 41, don't
Yep.
we have to unsquare root and multiply by 2?
Sure.
No,
We're gonna take 2
actually-
times the square root of 41, then you put it in your calculator. 2 squared root of 41.
Wait, doesn't it cancel off the square root and the...
They undo each other.
The square root of 41 is just 6.4.
Oh. So the square root of,
forgot the 2.
it'd be what? 12.8. So this is actually the biggest. Grade lied to us. Okay. So where should this 2 squared root of 41 actually go?
On the other side.
Okay, you guys can blame Graydon.
Well, actually,
What? That don't make no sense.
So 8 squared plus 10 squared equals 2 times the square root of 41 being squared. Thank you, Sarah, for catching that. Okay. So now we can test this out. 8 squared is 64. 10 squared is 100 equals 2 squared of 41. Well, that's 2 squared of 41 times 2 squared of 41, aka 4 times 41, which is what?
1, 6, 4.
164. So is this a right triangle?
Yes.
Yep. So what kind of triangle is formed? A right triangle.
oh, okay.
Wait, how did we get 4.41
Oh,
from the
wait,
64?
4 times 41.
And get the 4 plus 6.
Hey, that's a whole section.
I'll just go look on the video. Wait. 4? Oh, yeah.
Alright. So we had to reorganize that one because we found out 2 squared of 41 is actually the biggest side. But thank you. Thank you. But so it can still form a triangle because 8 plus 10 is more than 12.8. Okay, it's 18. So then as we went back through and we did the converse of the Pythagorean theorem, we basically just put it in the Pythagorean theorem to check. Okay. we end up getting this as our answer. We have to use the actual number. We don't want to use the approximate, because if we had used the approximate 12.8, we would not get that as a right triangle. We would get that as either obtuse or acute. We wouldn't get that as a right triangle. We need to go back through and use the exact one, the radical, when we go through and do our math. Okay? Here's our assignment. I'm going to be mean and not give any notebooks today. So heads up on the documents. Yep, and then as for simplified answers that are radical, so on numbers 19 and 20, it specifically says you can do nearest tenth. On the rest of them, I want radicals, or the whole number. No, on 19 and 20, it specifically says you can do nearest tenth.
Oh,